Yeah, today we will do on flow through flat plates, right? Flow through slit or flat plates. Those, as we mentioned in the previous class, that the flow through the homogenizing valve, this homogenizing valve can be assumed to be say slit, right, a very small hole through which it is moving, and during that process, as we said earlier, that the fat globules get homogenized, or the bigger fat particles becomes smaller according to the size which you have given, according to the space through which the flow is occurring, then that will indicate that at what ultimate size of the fat globules you will get, right. So, let us look into that today. So, now we have drawn one similar thing as it is here, flow through slit or flat plates, right. So, we have taken this to be enlarged figure of that slit, right. This is the enlarged view, and in which we have taken a small volume element, right. We have taken a small volume element, and this volume element has the dimensions of delta x, delta y and delta z, right, or say if the third dimension be delta z or h, and this width or one dimension could be 2 delta, so that the center is at plus minus del, right, 0 plus del minus del, and this is L and this is the height, right. So, we will do the similar force balances as we have done earlier, and we will find out what is the velocity profile and what is the stress profile in the volume element, and then integrate over the entire range, right. So, again this we have taken as 2 del. So, the axis is at the center. So, this is plus del and minus del, this is in the L length and height h, right. So, what is acting P at the pressure inside or inlet at P at x, and at the outlet at the face x plus delta x, it is P at x plus delta x, right. So, let us look into that. So, similar to the flow problems earlier we have done, right. Here also we assume some of the things that one is the flow is steady, then the flow is laminar, there is no end effect, rather it is fully developed, right, fully developed flow, and we will take a small volume, and that small volume is having del x, del y, del z, right. This del x, del y and del z, right, where we have shown this is the small volume, and the entire slit we had shown to be equals to 2 del, then L 2 del in this way, L in this way, and H in this way, right. That was the entire slit, right. Now, since we are saying that it is a steady state, then from the general equation which we start with, that the general equation or governing equation, that sum of the forces acting on to it is equals to 0, right. and that also we will do here. But since we said that momentum transfer takes place in two ways, one by the bulk molecule and one by the molecular transport. So, this bulk force, bulk fluid, that term goes off, right. Then we are neglecting that. So, unnecessarily we again writing everything momentum in minus momentum out for the bulk fluid, that we are skipping. So, we are starting with that the momentum flux right due to molecular transport momentum flux due to molecular transport, that we take as tau yx at the phase y plus delta y minus, this is okay, instead of flux we call it to be out minus in, right. Tau y plus at the phase tau y plus delta y times the area, that or rather tau y x at the phase y times the area, that is del at the phase del x into w, right. So, this is the area del x into w, this is acting, flow is occurring through this, right. We said the flow is occurring like that. Okay. So, this is the area del x into width, that is w or h, ultimately it will come, right. This is the momentum flux. So, pressure drop or pressure force acting on this volume element net is P at the phase x plus delta x, right, and minus P at the phase x, right, times the area, that is delta y times w, right. So, if this be true, then sum of the forces acting we can write tau y x at y plus delta y minus tau y x at y, right, plus P at x plus delta x minus P at x, this times delta y w, this times delta x w, right. So, now if we divide, this is equals to 0. If we divide both sides with del x w and y, then next stage we can write tau y x at y plus delta y minus tau y x at y over this we can say delta y minus P at x plus delta x minus P at x over, or this is of course plus, divided by delta x is equals to 0, dividing by del x del y w, right. Then we get this, and now if we put that limit condition, limit delta y tends to 0, right, and the limit delta x tends to 0 if we put, and then from the definition of derivative we can write that del del y of tau y x plus del del x of p del p del x rather is equals to 0, right. So, we can write del del y of tau y x is equals to minus del p del x, right. So, this del p del x we can write delta p over del x, that is delta p. Oh, actually this should have been written del y, this should have been written del x, right. So, this is del y, this is del x, exactly. So, yeah, this is del y, this is del x, otherwise this is not coming, okay. Del x, del y, this area, okay. So, this is 2 del which we ultimately said. So, delta p over this is del x if it is written like that. So, minus delta p over L is del del y of tau y x, right. Then we can now say that this negative sign or del del y of tau y x, this is equals to minus del p del x is equals to minus delta p over L. This indicates that as x increasing, right, as increasing at x increasing, value of delta p is decreasing. The negative sign says that, right, as L is increasing, delta p is decreasing, right. So, we can write that del tau y x again, that del tau y x, then we can say that d tau y x dy or del tau y x del y is equals to delta p over L. In this, delta p takes care of is equals to p in minus p out, right, over L. So, this negative sign is taken into delta p, right. Now, if we integrate, then what we get, that tau y x is equals to, right, delta p over L into y plus C1, right. So, what we can write at boundary conditions, if we put boundary condition, that is what, at y is equals to 0, y is equals to 0, if you remember our thing was like this, right, and this was like this, right. We said that this is 2 del, okay, del y, it was, this was del x and this was h or del z, whatever we call, right. So, at y is equals to 0, that means this point, at y is equals to 0, tau y x, that is the free end, right, not the wall at the center. So, tau at y is equals to 0, tau y x is equals to 0, right. Then we can write C1 is also equal to 0. or tau y x is equals to delta p over L into y. That is the stress profile, right. If we plot this stress profile, that as y is increasing, tau y x is also increasing, right. So, under limiting condition, that is when y is del, then tau y x will have 1 plus del. When y is equals to minus del, tau y x will have another, because this we have told ultimately the bigger one is 2 del, that is the thickness or width or whatever we call, right, where the axis is at the center. So, it is minus del, the plus del say this point and minus del this point, right. So, here it is 0. So, we write this. So, as y is increasing, tau y x is increasing, true, but it is putting to the limit when it is plus del, then tau y x is plus, and when it is minus del, tau y x is also some minus. That means some, if this is the point and if this is the point, this is 0. So, one will have 1 and another will have this, right. This is the stress profile. If we take this to be the stress profile, okay. Fine. Then substituting tau y x as minus tau y x is equals to minus mu del v x del y, right. We can write that this is equal to delta p over L into y, right. And if this is true, then again putting the second boundary, or now if we rewrite this, del v x del y is equals to minus delta p over L, right, or L into y rather, okay. Or we on integration we can write that v x is equals to this minus delta p over L into c, or rather y square by 2, right, y square by 2 plus c, y square by 2 plus c. So, if we put that boundary, what is the boundary? Boundary is at plus del or minus del v is equals to 0 or v x is equals to 0 at plus del or minus del, because plus del is at the wall and this minus del is also at the wall, right. So, in that case we can say that this plus del or minus del at plus minus del, this is equals to 0 v x. So, we can write 0 is equals to minus 0 is equals to minus, say plus minus del we have taken. So, we can write delta p over 2 mu L, this mu comes out, or here it should have been 2 mu. So, 2 mu L, right, 0 is equals to this is plus c. So, if we take minus, then c is equals to delta p over 2 mu L, right, and we can write v x is equals to delta p by 2 mu L if we take it to be common, right. Then we have said delta p, this was y, c and of course y square. So, it is del square, right. This was del square. So, c is equals to this into del square, right. So, if we take del square common or del square minus y square is the V x, right. So, or we can also write this is equals to delta p del square over 2 mu L into 1 minus y by del whole square, right. So, this is the V x at any instant velocity is like that. At any instant velocity is V x, that is delta p del square by 2 mu L into 1 minus y by delta whole square, okay, y by del whole square. Now, to understand for this next one, that is now at y is equals to 0, what is the value of V x? V x should become V max, right. I again for understanding put this, we had this delta x, we had this delta y, right. We had this as h or height or delta z, whatever we call, right. Then V at y is equals to 0, that is this, right. At y is equals to 0, we can say V x is V max, right. What we had this one equation V x is equals to delta p by 2 L 2 mu L into 1 minus y by del whole square, right, del square, right. This is nothing but parabolic equation, right. That is why the profile we always see to be parabolic like that, right. If we see the profile of velocity, it is always parabolic like this, right. So, this is also parabolic in nature. So, at y is equals to 0, then V max, V x becomes V max, and that is becomes equals to delta p into del square by 2 mu L, because this becomes 0, 1 minus this. So, that is 1. So, delta p del square by 2 mu L is the V max, right. Next, we go to the other one, that is the average velocity. So, V max we have found out, V we have found out, then from there we have found out V max. We have also seen the tau, and now tau means that is momentum flux. Now, let us go to find out average velocity. So, average velocity V average, that can be said to be equals to integration of 1 by a 0 to L 0 to del or plus del to minus del or 0 to del half of that V x dx dy, right. So, this is nothing but L over delta L, right, because one integration of dvx dx. So, that goes into this del. So, equal to L, right, 0 to L, 0 to del, right, y is there. So, V x dy we have L by del L, right, 0 to del V x dy we have, and this we can write L by del L, right, and V x if we substitute with this delta p del square by 2 mu L into 1 minus y by del whole square, right. This was between 0 to del, right, this into dy, right. So, this on simplification and integration and simplification we can write to be delta p, we missed out, oh delta p is there. So, that comes out delta p into del by L goes out 2 mu L, this comes there, and on integration dy is y, putting the limit is del minus this becomes del cube by 3 del square, right, del cube by 3 del square, or this is becoming nothing but equals to delta p del square by 3 mu L, because this del cube, this del square goes out, it becomes del by 3. So, 3 del minus del, that is 2 del by 3, right, 2 del, this 2 and this 2 goes out, this del becomes del square and this 3 remains, right. So, this is 3 mu L delta p del square by 3 mu L, right. And this, if you remember, we had made V max was delta p del square by 2 mu L. Then what is the relation between V average and V max? V average and V max, that relation becomes equals to V average is equals to 2/3 of V max, right. 2/3 of V max is the V average, right. So, this way if we can find out that what is the average velocity in terms of maximum velocity, it is 2/3. Now, if you remember what it was for the pipe flow average velocity with maximum velocity, what it was for the flow through or for film flow, and this is the slit flow, then these three you put together and see that there will be a distinct difference between the three, right. In one case it is pipe flow, in another case it is film flow, in third case it is annular flow, and in the fourth case it is that slit flow. So, all these four cases you just see what is the relation between V average and V max. In all four cases you will see they are distinctly different, right. In all four cases you will see that they are distinctly different, and I tell you that you find out and make a tabular form, so that you remember them for future activities, right, for future work or for in future, so that you can memorize it if required, that what is the velocity and maximum velocity relation in pipe or in annulus or in film or maybe in case of slit, right. And you will see they are not same, they are different. Okay. Now, let us look into that h we have said to be the height. Again we draw that h to be equals to the height, right. This was our h, and this h is quite bigger, right. H is much greater than 2 delta, right. So, in that case we can say that the hydraulic diameter for the slit that becomes equals to 4 del, right. So, we can say NRE this becomes 4 because we have taken hydraulic diameter to be 4 del because H is much greater than 2 del. So, hydraulic diameter becomes equal to 4 del. So, we can write 4 V average del rho divided by mu to be the Reynolds number. 4 V average del rho by mu, right. And fanning friction factor F we can write that is tau at wall W over rho into V by 2, right, or tau at wall is equals to delta P del by L, right, that is equals to 3 mu L V average by del square into del by L, right, that is equals to 3 mu V average by del, right. Therefore, F we can write delta P del over L over rho V average square by 2. So, this is 2 delta P del by L rho V average square. Therefore, delta P can be written 4 rho L by 2 del V average square, right. So, this can be also written 2F rho L by 2 del into V average square by 2, right. So, if you here it is 2 del, here it is 2, right. So, if we remember for the pipe flow what was delta P, right, that with F that was 4 F rho L by D V square by 2, right. So, that was for the pipe flow. So, this is also analogous. So, that is why these 4, as I said, that if you find out all 4, you will find it to be so different, and then you should have all these together in one page, and then it will be easy for you to remember. Okay? Thank you.